email. And I also want to point out that we'll have the form to suggest in-person speakers attached to every email that we'll send on Friday, announcing the next meeting. So ideally, if you have a visitor coming in, and you will know only later on in the springtime, you can still suggest it as a potential speaker. So take this in mind. Okay, so the first speaker of today is Konstantina. I'm not even trying to pronounce your surname. Well, you know Konstantina. Konstantina's research is primarily focused on the analysis of X-ray data, and her main scientific interest includes massive stars, galactic center, as well as X-ray binaries population and galaxies in nearby galaxies. She completed her PhD at the University of Crete in Greece under the supervision of Andreas Zetas. Subsequently, she spent 2 years as a postdoc at INAF Osservatorio Astronomico di Brera and 1 year at the Osservatorio Astronomico in Palermo. Since December, she has been working as a postdoc at CfA, continuing the same project she was involved in while in Palermo. And today she will be presenting part of this project. She also already visited the CfA, so maybe you already know her. So today she'll talk about EWOCS, the X-ray properties of the Wolf-Rayet stars in the young and very massive galactic star cluster Westerlund 1. Field is yours. Go.
Thank you, Andrea. Thank you all for coming. So yes, here I will present the very deep Chandra observations on the Wolf-Rayet stars in this massive star cluster in our own galaxy. And I will start with putting things into context. What are Wolf-Rayet stars? Wolf-Rayet stars are massive stars that they are evolved. They have typical masses of 10 to 25 that of our sun, and they're considered to be descending from O-type stars, which spend about 5% of their 5 million year lifetime in the Wolf-Rayet phase before their ultimate death as core collapse supernova. They exhibit very fast, Wolf-Rayet stars exhibit very fast dense winds with high mass loss rates, and they're known to be efficient dust makers, as you can see in this impressive image by JWST, where you can see the gas and dust nebula surrounding this Wolf-Rayet star 124. So as I told you, because of their very fast winds, Wolf-Rayet stars have characteristic broadline emission spectra. You can see 2 examples here. We usually see broad lines of helium since they're evolved stars, but also depending on what other kind of lines we see, we characterize them in nitrogen type Wolf-Rayet stars that have strong nitrogen broad lines. And these are the results of hydrogen burning in their core, while for carbon type or oxygen type Wolf-Rayet stars, we see the results of helium burning in their core. We see later the results in their winds with broad lines of carbon mainly. So why it is important to study Wolf-Rayet stars? Apparently, it's very important to study them because they provide crucial information about the final stages of stellar evolution, but also due to their high mass loss rate stellar winds and their ultimate death as core collapse supernova, they dominate the feedback to the local ISM in star-forming galaxies and overall help us understand their chemical evolution. So, but what about X-rays? From single Wolf-Rayet stars, we expect, in analogy to what we see for O-type stars, to see X-rays. We don't know the exact mechanism, but we understand that they come from shocks developed within the winds of the stars, and usually the spectra are very soft and thermal. What is the main difference compared to O-type stars is that because of the different chemical composition, the Wolf-Rayet winds are very opaque to X-rays. An example you can see in this plot here, where actually on the y-axis you see the stellar radius in logarithmic scale at which the opacity reaches unity. For example, for different type of stars, and on the x-axis you can see the X-ray wavelength. And for O-type system, the wind can be opaque up to 10 stellar radii, while for Wolf-Rayet stars, it can reach 100 up to 1,000 stellar radii, which makes particularly carbon type systems that you can see with the red line being very faint or even undetected when they're single in X-rays. But we also see X-rays from binary systems. Here's a model of a known Wolf-Rayet star, WR140. This is a system of a Wolf-Rayet star and an O-type star. And what happens here is actually when the winds of these two systems collide, their kinetic energy is transformed into heat, and X-rays are produced from the shock-heated plasma in the win-win collision zone. So in these systems, not only we have X-rays from within the single winds of the two stars, but also from the win-win collision zone. And the spectra are expected to be thermal, but harder. They have usually temperatures about 2 to 4 keV. An example you can see here for the same system. And the different colors of these spectra correspond to different orbital phases of the system. And what we can see is like characteristic lines of known elements. But also, very interesting, we see usually in colliding wind X-ray binaries, the iron line at 6.7 keV. This is iron 25, it's very ionized. And in order to get this highly ionized iron, we need to have very high temperatures. About 20 million degrees or even more, that we know that they cannot be developed in the winds of single non-magnetized Wolf-Rayet stars. So these two characteristics, the temperature and the iron line, could be used as a diagnostic to say if we have a binary system and colliding wind is in place. So what about the distribution of Wolf-Rayet stars in our own galaxy? We know that they are usually in or close to star-forming regions within the galactic plane. And we know that about 40% are in binary systems, although the number could be even higher. And the largest numbers of Wolf-Rayet stars are found in the galactic center, which you can see in this image here. This is a nice composite image of Chandra, Hubble, and Spitzer, and particularly in the star clusters, arches, and quintuplet that have 13 and 19 Wolf-Rayet stars, respectively. But also another massive star cluster in our own galaxy that has a large number of Wolf-Rayet stars is Westerlund 1. This is an HST image of Westerlund 1, and this is the ideal laboratory to study a large coeval population because it is considered to be formed in a single burst of star formation, and it hosts 24 Wolf-Rayet stars. And we have the unique opportunity to study this impressive massive star cluster through the EWOCS program, which is the extended Westerlund 1 and 2 Open Cluster Survey. PI is Mario Guarcello from the Observatory of Palermo in Italy. And for this project, we actually have very deep Chandra observations, which I'll be talking about later, for Westerlund 1 of 1 megasecond. We have 18 hours of JWST, and we also have 24 hours of Westerlund 2 in JWST and archival observation of Chandra about 400 kiloseconds. The main objective of this project is to study star and planet formation in these systems. And these indeed are the best targets due to their mass, age, and proximity. For more information, you can refer to the website of the project, but also to put back things into context regarding this talk, they host among the richest population of massive stars known. Let's concentrate on Westerlund 1. It has 166 massive stars, 24, as I told you, are Wolf-Rayet stars, 60 nitrogen type and 8 carbon type. And we have 4 of them firmly to be confirmed in binary systems, although the percentage is considered to be even higher. There have been previous studies in X-rays before the EWOCS data in Westerlund 1, 2 observations of a total of 60 kilosecond that reveal about 250 X-ray sources, and 53 out of the 166 massive stars, and 12 out of the 24 Wolf-Rayet stars presenting spectral information for only 5. This is quite impressive for a 60 kilosecond observation, but you can imagine what we will see with a 1 megasecond observation. And this is actually what we see. This is a recently published image from the work of Mario. This is the first publication through the EWOCS project. And indeed, we detect about 6,000 sources, increasing by a factor of about 25 the number of detected sources. And also we detect 126 massive stars. Now going to the Wolf-Rayet stars, we managed to detect 20 out of the 24. You can see them in this Chandra color image. And four of the four undetected ones are all of carbon type, which, as I told you before, usually they have more opaque winds, so we expect them to be fainter or undetected in X-rays. We reached down to luminosity limit of 10 to the 30, and we managed to extract X-ray colors for all the Wolf-Rayet stars and X-ray spectra. But what is interesting here is because of the long baseline of the EWOCS observation that span in 1 year and 2 months, we are able to search for periodic signals. And I will show you an example based on the brightest Wolf-Rayet star, WRA. We know about this star that is a confirmed binary with a nitrogen type Wolf-Rayet star and possibly an LED supergiant through infrared and optical data. Through optical data, also a period of about 7.63 days has been measured. And when we actually plot the light curve of the system with the EWOCS data, you can see on the top panel, we see that the source is obviously variable. But when we construct the periodogram, we find a very strong peak at 81 days, which is different than the one seen in the optical. Here I should note that the optical data have a baseline of about 20 days, so it wouldn't have been possible to see an 80-day period. But in order to see if another significant periodicity is hidden in this data, what we actually did is we fitted a sinusoidal to the light curve, we extracted this signal, and we reperformed the analysis, and we managed to recover the 7.7-day period, which was the strongest peak. So we can see that there are two periodicities in this system. One could be the orbital periodicity, or there could be a presence of a third body or something else going on within the wind of the massive star. We performed the same analysis for all Wolf-Rayet stars, and we found that all of them showed some kind of variability. We had clear periodic signals for 9 Wolf-Rayet stars, and we measured new periods for about 5 of them. So this shows that there is indication that all the systems could be in binaries unless something else is going on and reveals this periodicity. But in order to see that better, we need to look at the colors in the spectra. So I will go back to the color image of Chandra. And I know here that you cannot see very well what is happening. So let us zoom a little bit. And these are the Wolf-Rayet stars, starting from the brightest WRA to the faintest WRS. What is interesting in this image is that more than half of these stars appear to be very hard. They're blue, which is an indication of binarity. And this is confirmed if we place our sources on a color X-ray color diagram. You can see in this diagram the direction at which hardness increases. We have also plotted a grid, which you can see with gray dotted lines. This grid of simulated absorbed thermal spectra essentially gives us an indication based on the color of a source, what could be the spectral parameters. So what we can take out from this plot is that we essentially, apart for a very soft source that is WRH up in the corner, we can distinguish two groups. One is this group here that falls on the simulated grid. So these sources should have temperatures about 2 to 4 kV, which are typical for colliding wind X-ray binaries. And indeed, most of the confirmed binaries, which are shown with empty symbols, fall on this locus. But also we have another group down here where these sources seem to be quite hard and quite absorbed. So in this group, we have the two brightest carbon type Wolf-Rayet stars, and we have all the faint nitrogen type stars. So it will be interesting to see if this hardness is due intrinsically true, or is this due to higher absorption of the spectra, or what is happening. So let's look at the spectra. So here I show you the spectrum of the brightest source again, that I told you is a confirmed binary. We got the best fit model when we were using two thermal plasma model in non-thermal, in non-equilibrium. We got temperatures 2 to 4 kV, and we see the lines of known elements, and particularly we see the line of iron at 6.7 kV. But what is interesting here is that we kind of see two peaks there. So if we actually plot this in a smaller spectral binning to reveal more detail, this is what we get. And actually we detect two lines, one at 6.4 and one at 6.7 kV. What is interesting about these two lines is that they correspond to iron lines, but one is, corresponds to cold gas of neutral or low ionized iron, and in the other case, this corresponds to very hot gas of highly ionized iron, which indicates that within the wind of this massive star, there should be some cold gas that is getting photoionized by the hard photons from the wind-wind collision zone. So now let's have a look to the spectra of the entire population. And here are some examples of the sources that appear to be very hard. And indeed, we see that have very hard spectra with strong iron lines. And particularly in the system, you see a very strong iron line, but it's also very absorbed. But what is more interesting in all the spectra is that we see the iron line for the majority of these systems. In fact, for 17 out of the 20 of these systems and 19 out of the 20 of the detected systems have also hard spectra, which indicates that about 80% of the Wolf-Rayet stars in Westerlund 1, only through Chandra data, should be colliding wind X-ray binaries. But the question now is what happens with the remaining Wolf-Rayet stars? Are they all single system? Single stars. All of them are carbon type Wolf-Rayet stars. And there's another important characteristic of carbon type Wolf-Rayet stars that points to binarity. And this is that they can commonly produce dust. Here you can see two examples of carbon type Wolf-Rayet stars that produce dust. What actually happens there, and we consider like carbon type stars to favor the production of dust, is that when you have a binary system with a carbon type Wolf-Rayet star, you get the necessary ingredients. So you get carbon from the carbon type star, a hydrogen from the companion, and it's considered for the wind-wind collision zone to have the necessary density and offer also the protection from ionizing radiation to retain the dust. So going back to literature, we see that 3 of the 5 remaining systems are known dust emitters. So we consider them to be in binary systems. For the rest, the 2 remaining, we really don't know. We have no clue of whether they're in binary systems or not. So with this, we result that about 92 to even 100% could be in binary systems in Westerlund, the Wolf-Rayet stars in Westerlund 1. And this has important implication on the star formation channels and of binary systems and in general, star formation channels for very massive star cluster. And it's an important information that should be taken into account in any future modeling. That was it. Thank you very much.
Excellent. So questions?
Sorry. The 6.4 line in some of the system, would that be fluorescent out of dust grains?
Out of dust grains. I haven't really thought about it, to be honest, because yeah, like I was looking at the literature when fluorescence was found in massive stars, and the most common explanation was somewhere in the wind you should have cold gas that could be only unit temperatures larger than 7 kV, energies that larger than 7 kV to photoionize it. About the dust, I've never really thought about it. Let me think about it. Interesting.
Thank you for the talk. Could you go back to the slide where you had the grid of models and you had the data points with the temperature and the.
Yeah, sure.
So the
This one?
objects that are, yes, that one, the ones in the lower left there, so you didn't extend that grid of models to temperatures above, 4.8 in KT and 6 times, is that 6 times 10 to the 22?
Mm-hmm.
So I'm just wondering,
So-
how high does the NH have to be consistent with those
Yeah.
data? How high is the temperature?
If you see the actual grid lines, they change in size as you move down on the plot. So no matter how much I go down in temperature, you will not see much. There are many reasons that sources cannot fall on the grid. And for example, in this case, I'm using a very simple model for the grid, which is an absorbed thermal. Maybe these sources are better characterized by two thermal components and so on. So these are reasons that you could not see these things falling on the grid.
Yeah, I was wondering if you had other constraints on the neutral hydrogen column density that could help inform this, but.
In what sense?
Well, are there other measurements telling you where the column is?
We have one measurement for the column density towards Westerlund 1, which is quite high itself, but these are much higher. And indeed, I don't remember, like, if you see here, this particular system, you see how much absorbed it is.
Very absorbed.
So, yeah, I try to see how the absorption could variate, or the extinction could variate within the star cluster, but I didn't find any particular correlation. So yeah.
Any final question? You move to the double peaks of the iron line.
Yeah. There.
Yeah, so I was wondering, what model do you use to fit the iron line and what the iron abundance do you detect?
In this particular plot here, it's just a simple Bremsstrahlung and two Gaussian lines, just to see the energies. But normally, the iron line is at 6.7 kV is fitted by the thermal spectrum, the thermal model. Regarding the iron balances, usually the thing is, we were not able to really constrain the metallicity, especially for fainter sources, but for this particular one, they seem to be slightly supersolar. Yeah.
It's significant, because I see it's just seems a little bit above the, I don't know if it's thermal spectral, and I don't know.
Yeah, it's significantly detected. Thank you.
Curiosity of mine is that, how can you disentangle the amount of absorption when Chandra affected area and the soft range is so bad, especially because you're based your analysis on observations that took place in the last couple of years, right?
Yeah. What do you mean? How to disentangle?
Like, how can you be sure that those are really so absorbed and that you're just not missing something because you don't have affected area?
Well, if it's 10 to 22 or higher, Chandra can still get a decent strength. So that much absorption, Chandra can still be slower.
Yeah, I mean in that level. So yeah, thank you.
Excellent, let's move on then. So let's thank. Yeah, you have to do the number example with the presentation.
You already stopped the
Yeah.
sharing?
So in the meantime, the next speaker is Francesco Ubertosi. Francesco is finishing his PhD at the University of Bologna, where he works with Professor Miriam Gitti on EGN feedback in galaxy clusters. He previously visited the CfA in 2022, working with Gerrit Schadenberger and Ivan O'Sullivan on a study of jet reorientation in the central galaxies of groups and clusters, which he presented today. He's now visiting again until the end of February, so if you wanna talk with him, be faster. To follow up on the project is newly acquired high-resolution radio data. After this, he will return to Italy to defend his PhD thesis in mid-March. Good luck. And start a postdoc in Bologna, continuing his research on EGN feedback. So he's going to give today a talk with the title "Jet Reorientation in Central Galaxies or Clusters and Groups: Insights from VLBA and Chandra data." It is yours.
Okay, hi. So yeah, I'm very happy to be here again to present this project on which I worked on the last time I was here. I've mainly worked with Gerrit Schellenberger and Yvonne Sullivan, plus the other people you can see listed there. And if you're interested, we have recently published a paper on these results that you can find by scanning this QR code here or by looking for that reference. And I'm going to just go through a little bit of introduction on the topic and then move to the results of the paper. So let's start from what does it mean to observe AGN feedback in galaxy clusters. So in this sense, high-resolution X-ray observations are very helpful. And these are Chandra images of two galaxy clusters in which we have very clear evidences of AGN feedback. And what's the form of this evidence? So when I say AGN feedback, what I mean is jets driven by a supermassive black hole in an elliptical galaxy at the center of the cluster or of the group. In these cases here, we can see the sort of deficits in the X-ray distribution of the gas. And these are found on opposite sides of the bright source at the center. And the bright source at the center is actually an AGN at the center of the cluster. So actually, the radio band is gives us the range of frequency over which we are most sensitive to the jets driven by the supermassive black holes in the dominant galaxies of clusters and groups. And if we go to the radio band, we actually see that there is a very nice agreement between the jets and the lobes driven by the central black hole and these deficits in the X-rays. So basically these deficits, which we call X-ray cavities, tell us that these jets basically deposit a lot of energy inside the gas. And apart from these two examples, in the last 20 to 30 years, several other cases of this very good spatial match between radio and X-ray features have been discovered. And in particular, the picture that has come out is that jet activity by depositing energy into the gas basically prevents and regulates cooling of the hot gas of the cluster or the group. And so by basically combining the information from X-rays and radio observations, we can tell a lot about the nature of jet activity and how it impacts the cluster or group environment. And in particular, we find that AGN activity is transitory. So when we calculate the timescales of AGN activity using radio and X-ray observations, we find that the jet activity lasts for about a few tens of mega years. And after this time, the central engine greatly reduces its ability in driving collimated outflows. But that is not the end, because actually AGN activity is repetitive. So sometimes when we look at deeply observed systems, we see multiple X-ray cavities at increasing distances from the center. And this tells us that the AGN go through multiple phases of activity over time. And the nature of a jet is by itself also directional. So when we look at X-ray cavities, what we are doing is actually mapping through X-rays the direction of the jets that excavated those cavities over time. And if jets were stable and stationary systems, we should expect that over time, the direction of the jet basically keeps on pointing towards the same direction. And this is the case in many times. In this example here, I'm showing over there a very high resolution radio images of the radio image of the core of Hydra A, where we see these jets coming out of the core, which are very well aligned with what we see on tens of kiloparsec scales in the cluster, so the jets and lobes and the cavities. But this is not always the case. So there are systems such as NGC 5044, where when we look at the X-ray distribution of the gas, we see these well-aligned sets of cavities. But when we go to high-resolution radio imaging on parsec scales, we find a nearly orthogonal misalignment between the jets and the cavities, which makes us wonder what is the missing link between the two. And there are other examples. This galaxy cluster here, RBS 797, is a system that I've been focusing on during my PhD, and it shows these peculiar sets in the X-rays of perpendicular cavities on nearly the same spatial scales, which may suggest that the jet quickly change their direction very, very quickly to observe the cavities at the same distance from the center. And when we go to radio observations with kiloparsec scale resolution, we see this twisted morphology here that may be indicative of precession of the jet axis, which may explain the misalignment between the cavities. So it seems we got a nice picture of these systems, but the problem is that these misalignments have been investigated only in these very peculiar and well-observed systems, but we do not have any clue on the larger picture, right? So the problem is that we do not know if these misalignments are just very rare mechanisms that we observed in these systems, or if this is a much more widespread phenomenon. And this is important because if we want to build a comprehensive picture of jet feedback, we must have a good connection between what is the actor of feedback, that is the jet, and what is the smoking gun of feedback, that is the X-ray cavities that we observe in the X-rays, right? We also would like to know whether projection effects or environmental effects could have any major role in explaining these misalignments. So we would like to know whether external effects may explain all these cases or not. And if they not, we have to believe that the jets actually change their direction over time, which has something to do with the central supermassive black hole. But if so, how? The problem is that basically we know many mechanisms through which jets can change their direction over time, but these typically apply to systems where the accretion onto the supermassive black hole is very efficient, and it happens through a very thin disk that can cause torques and displacement of the spin of the supermassive black hole, whereas we think that the supermassive black holes in the central galaxies of clusters and groups are typically supported by very inefficient accretion that we do not know how could support a change, in some cases an orthogonal change in the direction of a jet in a very short time scale. So this is what we try to address. And we did that by building a sample, and we did that by selecting systems from a parent sample composed by Hogan and collaborators in 2014 and 15, comprising the 59 radio brightest central galaxies out of the BCS, EBCS, and Reflex catalogs of clusters and groups. And our selection criteria were to have extended jets on the parsec scales, so in VLBA radio data, and cavities in the X-ray Chandra data on the kiloparsec scales. And we obtained a final sample of 16 systems, which I know it's not a lot, but it should at least be representative of systems where AGN feedback is ongoing and it's vigorous, which is exactly what we want to probe. Okay, so I'll briefly show you what we did. So you have to imagine that the blue background here is the cluster gas. We identified cavities in the distribution of the intracluster or intragroup medium, and we measured their position angle with respect to the right ascension axis in the reference frame centered on the core. So for here, okay, when we move to the parsec scales, things get a little bit more complicated. So here, we basically did again the same thing. On parsec scales, we usually observe a core and at least another component, which is believed to be a jet, and in some other cases, a counter jet on the other side, okay? So we measure the position angle of the jets with respect to the right ascension axis in the reference frame of the core. But on parsec scales, relativistic effects become important. And in particular, one has that if the jets are slightly inclined towards the observer, the approaching jet is brighter than the receding jet. And one can use this information to constrain the inclination angle of the jets with respect to our line of sight, which gives us an idea of how much we are affected by projection effects on parsec scales. Okay, so here I'm showing the VLBA images for the high mass half of the sample, and I'm showing these because I think they're pretty, but also because you can see how we proceeded. We used the diffmap software to identify components in these images, so basically core and jets, and we measured the position angle of these components. So where is the jet located with respect to the core? And we did that for these systems here, and also for the low mass galaxy clusters and galaxy groups. And you can see that in some cases we have a core, which is usually the brightest component, and one jet. And in other cases, such as Able 496 over there, we have two jets emanating in opposite direction from the central source. And this is the comparison with the X-rays. Here are the Chandra images of the galaxy clusters in the sample. The green ellipses show the location of the cavities, and we actually had a lot of literature references on these systems pointing to the position and extent of the cavities already. And the white lines show the direction of the jets determined on parsec scales. So you can see that in some cases, such as Able 496 on the upper left side, there is a very good agreement between the direction of the jets on parsec scales and the direction of the cavities on tens of kiloparsec scales. While in some others, such as Able 2390 upper left panel, there is a 90-degree misalignment between the parsec scale position angle of the jets and the cavities on tens and hundreds of kiloparsec scales. So how frequent are these misalignments? Actually, they're not so rare. So basically here we're looking at the distribution of the misalignments. By misalignments, I mean how large is the position angle difference between the jets and the cavities, okay? So basically systems with a misalignment on the x-axis larger than 45 degrees can be seen as highly misaligned. And we see, by considering the full sample in the upper left panel and selected subsets in the other panels, that the fraction of objects with a misalignment larger than 45 degrees remains basically constant around 30 to 40%, which means that we find a probability around 35%, let's say, of observing a cluster or a group with a detected jet and a detected X-ray cavity, and find that the two are misaligned by more than 45 degrees. So it appears that misalignments are not so uncommon, right? They may be present in many systems. So when we want to look at the environment, the question is that basically we know that in these systems, there are usually bulk motions of the gas. One can have sloshing, which is an oscillation of the gas in the potential well of the cluster or of the group, but one could also have mergers between subclusters. And these may basically move the cavities around in the cluster atmosphere without actually the jets changing their direction over time. So we asked ourselves whether there was a one-to-one correspondence between systems with misaligned jets and X-ray cavities and systems with a dynamical perturbed environment. And it appears that no, because all of the systems are dynamically perturbed, even those that show a very good alignment between the parsec scale jets and the kiloparsec scale X-ray cavities. So it may be that the environment actually plays a major role at later times when the cavities become highly buoyant structure and very subject to the pressure gradients and density gradients in the gas. We also looked at that again at distribution. You may have noticed that there is this peak at large angles around 75 degrees. And this tells us that it seems to tell us that basically large misalignments are favored over smaller ones, right? So, but if the mechanism that causes the jet to reorient their direction was a random mechanism, we should expect a uniform distribution at large angles. But we observe this peak, and we actually find that it is significant at around 2.5 sigma level, which I know it's not a lot, but actually it is interesting because other works from the early 90s found very similar results using completely different objects. They focused on blazars, which are supermassive black holes whose jet actually point very close to our line of sight, so projection effects may be important. And they found again a peak in the distribution of the misalignments around 80 to 90 degrees. Okay, so we do have to do many more tests to confirm this, but it is interesting to notice this correspondence with earlier works. So we also looked at the time scales because it may be that only the very old cavities are misaligned from the very young small scale jets, but actually no, because we find systems that are already misaligned by nearly 90 degrees only 1 mega year after the cavities were excavated. So whichever the process is that changes the direction of the jet, it must be fast and occur on very short time scales. So I was saying before that it is typically believed that only systems with efficient accretion, only in systems with an efficient accretion, this can influence the spin of the supermassive black hole and drive a precession of the jet direction or a change in the jet direction. So we basically derived the accretion efficiencies of our system, and we found very low levels of accretion in our system. So it may be that there are very short periods of highly efficient accretion, but this must be short to allow the fact that we see misaligned cavities only 1 mega year after they were inflated. And we don't know how this could happen basically in this system. So if there is anyone who has any suggestion also on the theoretical point of view, it is very, very welcome. So I'm close to the end of my talk. I just want to point out that we found that misalignments seem to be quite widespread. We must absolutely continue to work on this to verify this point, but we find interesting suggestions that large misalignments may be favored over smaller ones, and we will do so because we were awarded 30 hours of VLBA observations to follow up on some peculiar objects in our sample, and we also plan to expand the sample to include as many more systems as we can. So thank you, and I'm happy to take questions.
Thanks, Francesco. Very nice talk. Questions?
I was wondering about the selection of the cavities.
Yeah.
And what it depends on. In UTC 5044, it looked like there were several other dark spots, for instance, if I don't know why they don't count as cavities. I'm sure you're reason.
Yeah, so there were actually many, let me just go back to the slide here. Okay, there were actually many works on NGC 5044 in the past, and in some of these, I don't remember which exactly, but in some of these, this one was counted as a cavity, in some other it wasn't. And also, yeah, there's also this other one here. Yeah, what basically helps us the most when having to deal with very sensitive observations that detect a lot of features there is the radio band, typically. So when we look at this system in the radio, there are very good indications that the radio source is covering these cavities and it's not covering this other one. But it is, I agree that it is in itself subject way of defining which are cavities and which are not. I still want to point out that if these were cavities, it would be even more interesting to know what has been going on in this system, because it would mean that there has been a mechanism that has excavated a cavity here, there, and there. So basically at the same distance from the center and a very short difference in time scale. So it may be that those are actually cavities. Maybe Iwan or Derek may have their idea on this, but in that case, I would find the problem of misalignment even more applied to this system.
So we have a question online by Dan Schwartz, which asks, what about dual IGN to explain the different directions?
Yeah, that is actually something that, so basically, if you assume that you have two active supermassive black holes in the core of the system, you don't have to basically require that the jets change their direction, right? But to have dual supermassive black holes in all of this system, is that viable? We should have to see some effect of a merger on the central galaxy. And in this case, NGC 5044, which is this one, is instructive because it has a very, its stellar component, it's not that much disturbed. It doesn't look like it had any major merger in the last couple of giga years. So while this may be viable in some systems, it may not apply to all of them. And also, if there were active supermassive black holes, if they were so common, we should have at least found one in our VLBA imaging data, right? Because we're looking at exactly at the space where we could resolve those systems, and we don't. So there must be something else, probably.
Any other question?
Nice talk.
Thank you.
I was wondering, so you describe how you get the alignment. Is there any other observational way to get this alignment?
So you mean measuring the position angle, or just knowing where the jet was in the past?
Yeah.
Well, sure, one could go for radio observations on kiloparsec scales. So if one had GMRT law or VLA, name your favorite one, one could forget about the cavities and just look at the radio, where the radio plasma basically was tens of mega years ago. But that would be interesting in itself, but we may start to miss the connection with the fact that we're looking for evidences of feedback. So we may step away from systems where we suppose there is this balance between cooling and heating. I don't know if this answers your questions, or you were looking for something more technical.
Yeah.
Okay. Well, we can talk about it.
Any final question for Francesco? What about the tidal disruption events to explain? Is sudden burst in accretion?
Okay. Yeah, it could be. I'm not that keen on tidal destruction events, I have to admit that, but
It's going to be rather massive black holes for that.
yeah, I mean the black holes at the center of these galaxies are around 10 to the power of 8, 9, etc. So yeah.
Okay, thank you. So let's thank our speakers again. I'm sure that Konstantina has more slots available for a meeting this week, while Francesco just said share my email that is down there, and it was also in the email announcing this seminar, so you just can meet within any time apparently.
Yeah. Well, it was just about today that this morning I had other meetings, but yeah, just write me an email.
Okay, see you next week.